talk about this offline because I'm also thinking about this aspect. Okay.
Thanks.
All right, let's thank the speaker again. All right, next up we have Florin Manea, who's going to talk to us about string theories and their relative power.
Yes. Thank you. So the paper is entitled on the expressive power of string constraints, and is common work with Joel Day from the Loughborough University in England, and Vijay, Ganesh, and Nathan Grewal from the University of Waterloo. And I am Florin, I'm from the University of Göttingen. So yeah, basically my talk will be about first-order logical theories based on strings or words. These are like finite sequences of characters, and they are over finite alphabets in general. And this has been a classical topic at the intersection of algebra, if you want to consider the free monoid, and combinatorics on words, automata theory, but also computability theory and complexity theory, as these type of logical theories were considered, for instance, by Davies, Putnam, Robinson in their attempt to show that Hilbert-Stan's problem is undecidable. In this area, there is a central concept, and this will be also a central concept for my talk today. And this is the concept of word equation, which essentially is the formal equality of two strings which are obtained by putting together string variables and string constants, so letters. And let me tell you more about these string or word equations. Essentially, as I said, it's a formal equality between two strings or sequences of characters, and these characters are constants, like the letters A and B here. So these are simply letters. They act like letters, and then you have X and Y, which are variables. So these are the usual semantic of a variable. They can be replaced by strings of characters, in general, in unrestricted ways. And now a solution to a word equation is simply a substitution of the variables, which makes the two sides of the equation actually equal. So we get this formal equality, and we transform it into an actual equality. For instance, in this case, we can simply replace X by B, so the constant string B, and Y by the constant string ABA, and you get two strings which are now actually equal. So AB, AB, and so on, in both sides. And the problem of deciding the satisfiability of word equations was actually a well-studied problem already in the 60s and the 70s. As I said, Davies, Putnam, and Robinson were trying to show that it is undecidable in order to use it to get that Hilbert-Stan's problem is undecidable. However, Makanin showed that this problem is decidable, in fact. And he gave a very complicated algorithm, which for a long while was hard to analyze, so people didn't really know the complexity of this algorithm. It was shown to be in p-space by Plandowski, and then this result was further improved by, for instance, Schulz in the 90s, who showed that even if you add additional regular constraints on the variables, you still get decidability. This means, for instance, you can say that X should be in this or that regular language. And finally, Arthur Riege proved in 2017 in an ICAL paper the fact that solving word equations can be done in non-deterministic linear space using a technique which is called recompression. However, this satisfiability of word equations is unknown, so the decidability status of this problem is unknown when linear arithmetic over string length is allowed. Of course, if you allow more than linear, so for instance, quadratic arithmetic, it's not hard to show that the problem becomes undecidable. But if you have linear arithmetic over the string length, then you still don't know whether this is decidable or not. So for instance, saying something like the length of x plus 2 times the length of y equals the length of z. So this type of linear equations. All right, so this is the status about word equations, and this, as I said, is a well-studied topic in theory, and there has been a renewed and recent interest in logical theories over strings coming from the area of string solving. So in general, string solving is a family of CSP problems which involve string variables. That is, variables whose domain is sigma star for some alpha sigma, so the words over some alphabet. But they also allow, we also allow variables over other domains, like natural numbers or integers, for instance, to model string length or string to number conversions and so on. And this area of string solving, so this study of constraint satisfaction problems, which involve string variables and string constants, found applications in the formal verification of, for instance, security protocols, so to detect, for instance, injections, but also in the symbolic execution or model checking of string-heavy programs. And there has been work in developing string solvers. For instance, there are string solvers included in general SMT solvers like CVC or Z3, but also dedicated string solvers like Ostrich. And together with these string solvers comes a relatively large set of benchmarks. So we have practical instances where we want to check the satisfiability of a constraint of a system of constraints which involve strings. So we are motivated in looking into how to solve word equations plus additional constraints, for instance, as I said, related to length. And there was a survey published in 2022 by Roberto Amadini, a survey on string constraint solving, so it suits very well our topic here. And one of the key takeaways from this survey was that there are actually 3 classes of constraints which cover the vast majority of benchmarks. And these are the word equations. And here we can even go a bit more fine-grained and say that we have concatenation as an operation to obtain longer string terms from variables and constants by simply concatenating them, and the equality between string terms. So, these are the key ingredients of word equations. Then a second large class of constraints is the membership to formal languages. And finally, the third one is linear arithmetic over string length. So you have these 3 classes. And of course, now looking at this from a theoretical point of view, we can actually consider logics consisting of formulas which are simply Boolean combinations of these general classes of string constraints. So for the rest of the talk, I will talk about string constraints of the following forms: word equations, denoted WE, which are simply formal equalities between strings which have variables and constants. Then length constraints, denoted len. So here I mean length function plus linear arithmetic between the length of different strings. They can easily be represented as the equality of the length of 2 strings by simply packing the constants as at the end of the strings. And finally, language membership constraints, and in particular for this paper and this talk, we considered membership to regular languages, membership to visibly push-down languages, and membership to deterministic context-free languages. So this is how I will denote them. And in general, when I will combine atoms of different types to get a formula, I will simply use a plus. So for instance, if I have something like WE plus reg plus len, this means that I will use word equations as atoms, regular membership constraints, and length constraints. We will see more examples in a second. For instance, here you have this formula. Maybe here 2 points would have been better, or colon or so. So here we have a word equation, x1 ab x2 equals x2 ba x1. the variables are x1 and x2. And then we have here some length constraints. The length of x1 plus 2 equals the length of x2. And here you have a regular membership constraint, which just says when we will replace x1 by using a substitution, we can only substitute x1 with a string from this regular language. Obviously, we use word equations, regular constraints, and length constraints. Therefore, this formula is in WE plus reg plus len, but it's not in WE plus reg due to the occurrence of this length constraint. Okay, so in general, as I have said from the beginning, the typical string solving question would be satisfiability. So let phi be a formula, for instance, from WE plus reg plus len, and we are curious if there exists an assignment, or does there exist assignments of the variables in phi such that phi becomes true. So this is, as I said, well, in some cases undecidable, in some cases decidable, in cases like the theory here, it's unknown the status of this problem. So we tried to look at this problem from a different perspective, namely trying to understand the solution sets for formulas from different theories. So for instance, we considered this expressive power question, let phi be a formula in one of these string-centric logics, for instance, the one with word equations, regular constraints, and length, and let x be a string variable occurring in this formula. And then we can define the language expressed by this variable x in phi as the projection of the solution set on the variable x. So these are essentially the words which can be used to substitute x and then still extend this substitution to a solution for the entire formula. And in general, we will say that a language L is expressible in such a logic if there exists a formula phi from that respective logic and a variable x in that formula such that the language is exactly the language expressed by that variable in that formula. Okay, and general, let me just quickly recap what I have told you so far. We have seen what means that the language is expressed by a formula. It means that there is a variable in that respective formula such that L is the set of all values for which there is an assignment mapping x to that respective value, which makes the formula true. And our theories are, as I said, word equations, or word equations plus additional constraints. And for instance, just to see some examples, this language a to the power n, b to the power m is expressible in word equations by a variable x. You simply say that x is the concatenation of two variables, z and y. Z will be the a's, y will be the b's. And then by saying za equals az, you enforce that z is a repetition of a's. And you do the same trick for y's. So this is done by word equations alone. You can also do more complicated stuff, like, for instance, WW, where W is from some particular regular language. So you don't really need all the time to use these regular constraints to enforce the membership in some regular languages. However, sometimes you might have to do, so you might have to use additional constraints. For instance, a to the n, b to the n can be expressed by word equations plus length. The first part is the first trick that we have seen here. So a to some power, b to some power, and then using length, you can enforce that these powers are the same, these exponents are the same. And finally, there is here an interesting example. For instance, you have the language which contains some words made up of a's and b's, then a new letter c, then some other word made up only of b's. Well, this is expressible canonically in word equations plus regular constraints, and we will see that, for instance, this is not expressible by word equations in a bit. So here are some examples of languages which are expressible in these theories. You see the general story is that we define a variable in which we collect basically exactly the words of the language that we want to express. And What are the questions that we have considered here? We have considered 3 questions. I will only talk about the first one, and I'll try to do it relatively quickly. For 2 logics, how do the classes of languages expressible in the respective theories or logics compare? And what are the consequences of such results? Then the second question is, given a logic, how does the class of languages expressible in that logic compare to the Chomsky hierarchy? So a typical language theoretical question. And what are the consequences, for instance, with respect to satisfiability for formulas in that logic? And finally, the third question is a bit more complicated. Given a language L, which is expressed by some formula from a logic, let's say logic 1, and the second logic, which is usually simpler, can we compute a formula from the second logic such that the language expressed by a variable in that formula, here should be phi prime, is exactly the language that we started with? And this is interesting from the perspective of string solving, so from an actual practical perspective, because basically maybe we want to compute some sort of normal form for our formulas. I have a formula that's very complicated, mixes up various constraints. Can I reduce it to some simpler set of constraints? Can I work in that direction? This is something that string solvers actually do. They take complicated constraints and they try to rewrite them as word equations or language membership constraints. And basically, we wanted to see in which cases this can be computable. And what we got is this picture, so zoo of theories. The idea is that we have quite a few theories on the upper part, which are all very complicated, and they express all recursively enumerable languages, which of course tells us that the satisfiability problem and many problems for those logics will become undecidable. And then we have on the left part several classes of, or several logics which involve word equations which do not express all recursively enumerable languages, and moreover can be strictly separated among them. And on the right-hand part, this is something more interesting, for instance, for people working in language theory or in automata theory. You have some theories which are related strictly to formal languages, and they do not include word equations, so they don't have equality between string terms. Okay, the main results of this paper are, of course, those which also consider word equations. And there are 2 classes. On one hand, we have the characterization that these logics on the upper part all express all recursively enumerable languages. And then we have the separation between these logics on the lower part. All right, first theorem. The class of languages expressible in the family word equations plus visibly pushed down languages is exactly the class of recursively enumerable languages. This actually is one of the theories here, this one. And we actually prove a stronger result. We do not really need string equality to get this theorem. It's enough to consider membership to VPL and concatenation. Otherwise, the proof idea is quite standard. You encode computations of a Turing machine in such formulas, and then use one variable to extract the input strings for such accepting computations of Turing machines. And as a consequence, as I said, the satisfiability, for instance, in word equations plus VPL is undecidable. That's interesting, again, for string solving, because this VPL membership is something that is very close to regular membership plus length constraints. So it extends this, class that we do not know anything about just a bit, and you already get undecidability. Maybe that's a sign that satisfiability for that problem is also undecidable. But this is something that we do not know yet. And the second part of our, main result bunch is that basically we show some inexpressibility arguments to separate these classes. And I will go very quickly through that. Essentially, if you have a word equation, you can write its solution in this way. So, you have the image of the left side here, the image, so here is the left side, here is the right side, and you write it, like corresponding letters. And the trick here is that you can partition the positions of a solution in groups of linked positions which take the same value. So for instance, here we have an A. This means that on an upper part we will also have an A, but this is, it's the first letter of X. So also in the upper part where we have an X, we will also have an A, and so on. You get sort of a link between these positions. So for instance, after several steps, you see that if in one of these positions you have an A, then in all of them you will have an A. And the trick coming from a paper from 2000 is that it might be the case that this group of linked position is actually not determined by any, it's not determined by any actual constant from our equation. So for instance, here we have that this position is determined by this W. This means that we can put there an A, but we can also put anything that we would like. So we can put any other word, right? So this means that, the skeleton for the solution of this equation is actually, you have some positions like these B's which are determined, but all the others could also be replaced by something else, with the only restriction that you should have the same something else everywhere. And yeah, basically you can then just replace this with whatever you want and get a new solution starting from an existing one. And this was used by Karhumeki, Minyosi, and Plandowski as a sort of pumping argument. So can we use this to show that some languages are not expressible by word equations? And the idea is a bit complicated, but it resembles a bit this general pumping lemma that we use for regular languages, for instance. You want to show that a language is not expressible. You assume, for the sake of a contradiction, that it is expressible. Then you choose some good factorization scheme for this language. For instance, separating a word into blocks of letters, so just grouping together the same letters, something that always works. Then you pick a long word in your language such that this word has many different factors. And now the trick is that if there are enough different factors in the long word that you have picked, then at least one of them will be unanchored, meaning that you could actually replace it with something else and still get a solution of the same equation. The idea is that really if you have very long solutions for a short equation, you can imagine that big chunks of that solution will be just overlaps between themselves, but they will not be connected to any constant. So somehow, once you isolate these parts, you can freely replace them. And then you can swap them with something that, breaks the properties of your language. That's pretty standard, like usual pumping lemma algorithm. And you get a solution which is not in the language and therefore a contradiction. For instance, in this way, one can show that if you want to express the language, the language of the words over ABC, which have at least one, which have no C in them, then you can do that. Essentially, you will just take a long word like here, this one. It has, a long factor. It has long factors in its factorization, and then you can identify one of these factors, swap it with a C, and there you go. You should get a solution to your equation, but it's not from the language. So very simple languages are not expressible by word equations. What we do is depicted here. We simply identify the factor which we were then able to switch. The same works if you have length constraints. The only trick is that when you swap factors, you need to be careful to preserve the length. Otherwise, the equation stays the same due to this pumping argument. The length of the solution stays the same because you didn't change it, actually. And you can, for instance, show that the same language that we have seen before is expressible in so in word equations and regular constraints, but not in word equations and length. This can be adapted to work for regular constraints, but there you need to be a bit more careful. And we also made it work for word equations plus length plus regular constraints. The only difference was that in this time, our argument did not go in the direction of breaking the structure of the language, but it had a more combinatorial flavor. We started with a language that has a certain growth rate, and then we showed that we can actually increase the density of this language by pumping, and basically we will break this solution or this property by simply, producing more words in the language. So they might have the same, nice structure that we want in our language, but there will simply be more, and this led to a contradiction. I just will finish now. I won't go through all these details. You can see them in the paper. I'll just leave you with this separation and grouping of theories, and I invite you to look in the paper how this, separation between different logics from a language theoretic point of view actually lead to various decidability properties and various, let's say, properties which could be relevant, for instance, for string solving in practice. Thank you.
Thanks very much. While you're setting up, we have maybe time for one very quick question.
Hi, I'm Ankit from Northeastern University. Thanks
Hi.
for the great talk. So do you have any result about how many unanchored blocks can be found given some number of factors in a given word equation? Like if we replace x by, say, 10 factors, a concatenation of 10 factors, then what is the expected number of unanchored factors?
Sorry, can you?
Do you have results of the form that given this many factors in a variable, we can find X number of unanchored blocks?
I think it's a good question. We do not have this type of results in this paper, but I think that people are looking into that, so somehow understanding better the combinatorics of these factors inside the solutions. I think it's actually, so there is this paper from Karchumeki, Mignosi, and Plandowski from, I think it's JACM 2000. That's where they started the study of these unanchored factors. So maybe have a look there. I don't think that they have, very many results in the direction that you are curious of. But I mean, we can take this offline. So
thank you.
Thanks.
Let's thank the speaker again.